Okay, welcome back, mathletes. Today we are going to be taking a look at the team round of the 2024 State Math Counts competition. Please check out my other videos. Don't forget to like and subscribe, and let's get right into it here. So problem 1 said Aaron's fastest centipede can travel 19 and 17/25 of an inches per second. So that's in inches per second. And at this rate, how many miles can Aaron's fastest centipede travel in 2 hours? Express your answer as a decimal to the nearest hundredth. Okay, so we need to convert inches per second into miles per hour, and then we need to multiply by 2 hours. So let's see, we can start by, basically it's a unit conversion problem, and I like to think of these unit conversion problems as just multiplying by 1 in different units. So for example, we could multiply by 1 foot divided by 12 inches, right? Because 12 inches is equal to 1 foot, so this is just like multiplying by 1. And then we can multiply by 1 mile divided by 5280. You just kind of have to know that that's the number of feet in a mile for this problem. Unless you happen to know how many yards are in a mile, you could also multiply that by 3 to get this. All right, the next thing is to worry about converting the seconds into hours. So you could multiply by 60 seconds per minute and then 60 minutes per hour, or you could just multiply by the number of seconds in an hour. So there are 3,600 seconds in 1 hour. And then now we need to multiply by 2 hours. And what you'll find is that the inches cancel here, the feet cancel here, the seconds cancel here, the hours cancel here, and we're just left with a number of miles, which is what we wanted. We wanted to know the number of miles. So all we got to do is get out our handy calculator, which is allowed on the team round. And we just need to compute this. So we have 19 plus 17 over 25. That's our speed in inches per second. And then we're going to divide by 12, divide by 5280, multiply by 3600, and multiply by 2. And that's going to give us 2.236. But we have to round that to the nearest hundredth, so it's 2.24. 2.24. That's equal to 2.24, and the units here are miles. That's our answer. We could pop that up in here. All right, great. That wasn't too bad. The next one says Beatrix is buying carrots to feed the rabbits in her garden. Every 5 carrots she buys at the regular price from Carrots R Us, she can buy a 6th carrot for 15 cents. If Beatrix buys 12 carrots from Carrots R Us for a total of $2.60, what is the regular price of a carrot in cents? So we're going to do everything in cents. I'm just going to call this 260. All right, let's take a look. So 5 times the regular price plus 15 cents. If she spent that amount, she would be able to get 6 carrots, but she bought 12 carrots, which is twice that amount, and she spent 260 pennies. So we're doing everything in pennies because that's what it wants in the end is cents. All right, so we divide by 2. Actually, we can divide by 10, right? Because 2 times 5, we're going to divide by 10. So this is going to be 26, and this is going to be P plus 3. P plus 3 is 26, so P is equal to 23 pennies. 23 cents. We can put that right up here. Okay, that wasn't so bad either. This one says Aditya writes down some of his favorite numbers. Every number on his list is a prime number, and no two numbers on his list share any digits in common. What is the greatest possible number of terms in Aditya's list? Okay, so we would really like to use numbers with a low number of digits and have them be prime. So we might choose 2 and 3 and 5 and 7. 9 is not prime, so we can't use 9. But we could use 19, for example. But if we use 19, then we're using our 1. We could also do 11. I guess we could choose. We could either choose to use 19 or 11. But if we use 11, maybe we can think of another number that ends in 9. So let's use 11. That way we're only using one digit here. So what digits have we not gotten yet? Well, we've gotten all the odds except for 9. So we're looking for something that might be able to use a 9. And we got 2, which is the only even prime. We're not going to be able to get the even numbers unless they're, except if they're in the tens place other than 2. But we could try to use an even number with a 9. So let's see, 29 wouldn't work because we already have a 2 here, unless we want to give up that 2, which wouldn't be nice. 49 is not prime, so we can't use that. 69 is also not prime. And 89 might be a possibility. Yes, 89 is prime. So that one's good. So here we've got 6 numbers, and we haven't used any digits more than once. We've used 1, 2, 3. We haven't used 4. We haven't used 6. We've used 5, 7, 8, 9. So 4 and 6 are the only 2 digits we haven't used. But we're not going to be able to get a prime number just using these digits. So I think we're done. We've got 1, 2, 3, 4, 5, 6 terms. That's the max we can do. All right, great. Now, I'll just make one comment here. I did get a chance to be one of the graders at the State Math Counts. And when I looked at the team that I graded, they got these first 3 problems all correct, and they missed all the other problems. And the person that was sitting next to me grading had the same thing. The first 3 problems were correct, all the other problems were wrong. And I think our school's team had maybe the same score. But anyway, the first 3 problems were definitely the easiest ones. So now we're going to get into the harder ones a little bit. This says, in the exciting new game of hyper football, 2 teams compete against each other for points. The only way to score points are by getting a touchdown, sounds like football, a smackdown, or a shutdown, worth 6, 10, and 15 points respectively. What is the greatest integer score that a team cannot have during a game of hyper football? Okay, so we've got some a times 6 plus b times 10 plus c times 15 equals our total score. That's a is the number of touchdowns, b is the number of smackdowns, and c is the number of shutdowns. And that'll give us our total score. We want to know the highest score that you cannot possibly have. So for example, you couldn't have a 1, right? You couldn't have a 2, 3, or a 4. In fact, you couldn't have a 5. But you could have a 6, right? But we want the highest one that you can't have. So for example, so we can keep going from that. One thing I'll point out is that just by using the smackdowns and the shutdowns, we can get almost every single multiple of 5. So we could get 10, we can get 15, we can get 20 by using 2 of these, we can get 25 by each of these. And you can see pretty quickly that by combining these, we can get everything except for 5. Now, and I guess 0 you could get by not having anything. But so really 5, maybe what I'll do is I'll keep track of the scores that I can get for different values of A. Because A is kind of going to determine what the score is mod 5. Right, so let's say I could be 0 mod 5, I could be 1 mod 5, 2 mod 5, 3 mod 5, 4 mod 5. Those are my possibilities. What I mean by mod 5 is that these are the remainders you can have if you divide your score by 5. So for 0, we could get a score of 0. We cannot get a score of 5. We can get a score of 10, we can get a score of 15, and so on. All these other ones we're going to be able to get. So far, the highest score we can't get is a 5. Now, what about for mod 1? You can't get 1. You can get 6. You can't get 11 because that's 5 plus 6. 16, you can get, right? You just have a touchdown and a smackdown. And then everything else, 21, it's going to be some multiple of 5 that we know we can get, plus 6, right? So these are all going to be good. So now 11 is the highest that we can't get. What if we go to 2 mod 5? Well, we can't get a 2, and we can't get a 7, but we can get a 12, right, by doing 2 smackdowns. And then we can't get a 17. And then we can get, I think we can get a 22 by doing 1 smackdown and 2 touchdowns. And all the other ones we're going to be able to get. Because what's happening here is basically this mod 5 is our A. Or our A could be some multiple of 5, more than that. But basically if you have A equals 2, you just pick the multiple of 5 that you can't get. Which is, so 2 of these is 12, plus 5 is 17. So 0 of these is 0, plus 5 is 5. 1 of these plus 5 is 11. 2 of these plus 5. 3 touchdowns is 18, plus 5 is going to be 23. So that's going to be the highest one we can't get here. 4 touchdowns is 24, plus 5 is 29. So 29 is going to be the highest one that we cannot get. There's no way we can get 29 by combining these, because we know that we need at least 4 touchdowns to get 29, and that gives us 24 points, plus you need another 5, which you can't do from these. All the other ones up above you can get, because you can get 4 touchdowns plus 10 points by getting this, or 15 points by getting this, and so on. So that's one way at least to do that one. That gave us 29 points as the highest score you cannot get in hyper football. All right, moving right along, we've got a square ABCD. Okay, we've got A here, and it's a square. We've got B here, C here, and D here. That's our square ABCD. And what else does it ask us? It says, well, it says it has side length 14, so let's write 14 for the side length. Then it says there's a point P that lies in the interior somewhere, so that AP is 15. Okay, so it's 15 away from A, which means it's somewhere along here. And it's 13 away from B. So it's probably somewhere around here. But it's 15 here, 15, and it's 13 here, 13. Okay, what is CP? Okay, this is P here. It wants to know CP, that's this distance. All right, so what we're going to have to do is we're going to have to figure out, I think we're going to have to figure out the height of this triangle here if we drop an altitude. So the base is up at the top here, 14, and then we drop this altitude. One thing we could do is we could call this X here, and we can use Pythagorean. If this is X, this will be this bit here will be 14 minus X, right? So let's do a Pythagorean theorem on these 2 right triangles here. So we've got this leg equal. This leg is obviously the same between those 2 right triangles, so we can set those equal to each other. One of them is square root of 15 squared, which is 225, minus, let's see, square root of 15 squared minus x squared. Is that right? That's going to be equal to the square root of 13 squared, which is 169, minus 14 minus x squared. I'm running out of room here. I'm just going to put it down here. 14 minus x quantity squared. That's supposed to be up in here. All right, so we can square both sides, and we have 225 minus x squared equals 169 minus 14 squared is going to be 196. And then we'll have a minus 28x, but since it's minus that, we're going to have plus 28x. And then we're going to have, this is going to be plus x squared, but it's a minus, so it's actually minus x squared. That minus x squared is going to cancel with this one, so I'm just going to cross out that one. All right, great. Now let's see, we got 169. We got 225 plus. Well, what the heck? Why don't we just use our calculator here? We've got 225 minus 169 plus 196. That's what's going to be on one side, and we're going to have to divide that by 28 to get x. So 252 divided by 28. It's going to give us 9. So x is 9. All right. X is 9. Oh, and we could have probably seen that because this is a 3, 4, 5 triangle, isn't it? This is going to be 12 here. Just to be clear, this 13 is this one, and this is a 5, 12, 13 triangle, because 14 minus 9 is going to give us 5. So we have these two familiar Pythagorean triplets here. This one's a 3, 4, 5 scaled up by 3, and this one's a 5, 12, 13. So what that means is that this is 12. That means this distance from P down to here is going to be 2. And also this distance across here has got to match this one, which is 5. So now this distance CP is just going to be easy from the Pythagorean theorem. We're going to have the square root of 2 squared plus 5 squared, which is the square root of 29. All right, let's move right along to the next problem. So this one's problem 6. It's a tricky one. It says a geometric sequence has 20 terms. The product of every fourth term starting with the fourth term is 32. The product of every fifth term starting with the fifth term is 4096. The product of every third term starting with the third term can be written as 2 to the k, where k is an integer. What is the value of k? So let's see if we can write this out. The terms of this geometric sequence are going to be some constant is going to be the first term, and then the next constant is going to be multiplied by some ratio. So we could say k times a ratio. And then the next one is going to be that original constant times the ratio squared. And then, so this is term 1, term 2, term 3, and so on, all the way up to term 20, which is going to be k times the ratio to the 19th power. So what am I going to get if I take the product of every fourth term starting with the fourth term? Well, the fourth term is going to be k times r cubed, and the next one, if we're doing every fourth term, is going to be k times r to the 7th, and we're going to continue on. How many terms are we going to have if we do every fourth term starting with the fourth term? Well, there's 20 terms. We're going to have 5 terms. So we're going to end up with k to the 5th. I'm not going to write this all out, but it's going to be equal to k to the 5th power times r to the, and we're going to add up these exponents since we're multiplying all these r's. So we're going to have we're going to have r to the quantity, 3 plus 7 plus 11 plus 15 plus 19. 19 is the last term, is the exponent of the last term in our sequence. So this is, let's see, that is equal to 32, right? Yes, that's equal to 32. The next thing they told us is that the product of every fifth term starting with the fifth term is 4096. So how many terms are there going to be? So there are going to be 4 terms because they're going to have the 5th, the 10th, the 15th, and the 20th. So we're going to have k to the, what did I say? 4 terms, right? K to the 4th times r to the, so the 5th term will have an exponent which is 1 less than 5, which is 4. So we're going to have 4 plus 9 plus 14 plus 19. Okay, so this is going to be k to the 4th, whoops, k to the 4th, and r to the, what is this, 13 and 14 is 27, 37, 46. I think this is the 46th power, if I'm not mistaken. All right, so now we have, let's see, I'm going to simplify this as well. So this is 10 plus 11 is 21, 36, 40, 55, I believe. This is going to be 50, it's going to be to the 55th power. So this is k to the 5th times r to the 55th. Yeah, thanks. So then this one is equal to 4096. I'm just going to write that as 2 to the 12th. And maybe I'll write this one actually as 2 to the 5th power. All right. So then we have, so what I'm going to do with these two is I'm going to say, all right, we don't know what k is, and we don't know what r is, but whatever they are, they have some log base 2. In other words, we could write k. I'm going to write this. I'm just going to write this up. Let's see. I'm going to write it up above here. K can be written as 2 to the a. We don't know what a is either, but it's the log base 2 of k. And then r could be written as 2 to the b. The reason I'm doing that is I want to be able to just add these exponents to what's over here. So in other words, if I do k, which is 2 to the a to the 5th, that is just going to be, well, let me just write it in this spot. That's going to be 2 to the 5a, right? 2 to the 5a. And when I have 2 to the b to the 55th, that's going to be 2 to the b times 55. B times 55. And that's equal to 2 to the 5th. So now I know that if I add these exponents, I know that 5a plus 55b is equal to 5. Okay, so that is really helpful. I'm going to be able to solve for a and b if I get another equation like this, and that's what I'm going to get here. So this one is going to be equal to, k is 2 to the a, so we have 2 to the 4a, and then we have 2 to the b to the 46th, so that's going to be 2 to the 46b. All right, and that's equal to 2 to the 12th. So we have another equation here. We have 12 is equal to 4a plus 46b. All right, so we can solve now. We can solve for a and b because we have two equations and two unknowns. And let's see, maybe we can divide this equation by 5 since everything's divisible by 5 there. We have a plus 11b equals 1. And this one we could divide by, well, we could divide it by 2 at least. So we have 6 is equal to 2a plus 23b. So 2a plus 23b. And maybe to get rid of the a's, what I'll do is I'll multiply this equation by 2 and subtract this equation. That'll be 2a minus 2a gives me 0a, which is what I wanted, and it'll have 22b minus 23b. That gives me negative b, and that is equal to, let's see, 2 minus 6 should be negative 4. So that means b is equal to 4. And now I can plug that in back in up here. If b is 4, I have a plus 44 is 1. So if a plus 44 is 1, that means a must be negative 43. Okay, so we've got a and b. And now we can go and look at what every third term starting with the third term is. And we should be able to figure it out now that we know what a and b are. Okay, so let's make a little room. Make a little room over here. And grab ourselves another color. Oops, let's see. Okay, so what have we got? Every third term starting with the third term. How many terms is that going to be? It's going to be 6 terms, so we're going to have k to the 6th power times r to the, we're going to have the 2nd power for the third term, right? And then plus 5, plus 8, we're going up by 3 every time, plus 11, plus 14, plus 17, and we don't do plus 20 because the highest power we have is plus 19. Those are going to be our 6 terms that we're adding up. So we need to add these all up. Let's see, this is 15, plus 11 is 26, plus 14 will give me 40, and then 17 is 57. So now I have k. Remember, k is 2 to the a, so this is 2 to the 6a. And r is 2 to the b, which is, oh wait. Well, okay, why don't I just fill in a, because I know what a is. So 2 to the 6 times negative 43. That's k to the 6th. And then r is 2 to the b, which is 2 to the 4th power. So we have 2 to the 4 times 57. And that's going to equal 2 to the k. And what they want to know is what k is. So that's 2 to the k. And now we just have 6. We'll just grab the calculator since we have it for the team round. We have k is equal to 6 times negative 43 plus 4 times 57. and that's negative 30. So the answer here is negative 30. Negative 30 is our answer. All right, so we've got done with 6 problems. Let's move on to number 7. Okay, this one says the arithmetic mean of a set of distinct prime numbers is 31. What is the greatest prime number that can be in this set? Okay, so all the prime numbers are obviously going to be positive, and we've got the mean is 31, right? So that means we have to kind of balance out all the stuff that's below 31 with all the stuff that's above 31. And we want one of the numbers to be as high as possible. Right? We want it to be as far this way as possible. So what we want to do, if we want to go as far this way as possible, we want it all to balance. Just imagine this is like a scale, and you've got the balancing point at 31, and you want to put 1 as far up here as you can out on the right side. You're going to want as much weight on the left side as possible. So all the prime numbers that we have that are less than 31, if possible, we want to add them, we want to put them on to the scale here. So we've got 2 and 3 and 5 and 7, 11, 13, 17, 19, what's next? 23. I'm going to make another row maybe. 29, and that's the last one, right? I almost had enough room. Okay, so if I put all these together, and then I have some number x out here that's also prime if I'm lucky, and I average these all together, I'm going to get 31. Well, what does that mean? That means that, how many numbers do I have all together? I have, over here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I add this x over here, I'll have 11. So that means the sum of all these numbers has to be 31 times 11, right? So 31 times 11 is going to be our sum. So that's 341. So if I subtract from 341 all these prime numbers over here, that'll give me x. So 341, and then we're going to have to see if that's prime or not. So we subtract all these primes. 2 plus 3 plus 5 plus 7 plus 11 plus 13 plus 17 plus 19 plus 23 plus 29. That's going to give me 212. Okay, that's definitely not prime, right? Definitely not prime. 212. This would be 212. So we got it to balance, but we need to only use prime numbers. So we need to change things around so that we can have this higher number be a prime. How are we going to do that? Well, imagine you cross out one or more of these primes over here. If you cross out, for example, the 29, that will move this 212 down to 210. Because this 29 was 2 less than 31. So, you're kind of giving up something that's pulling you in this direction by 2. So you have to kind of give up on, we have to move this back in this direction by 2 as well. Now, that's not going to help us because since that distance there was an even number, that means I'm going to be changing by an even number here, and it's still going to be an even number. In fact, any of these primes that I take away are going to make it go down by an even number, except for this one. So I know I have to cross this one out. So what's that? That's going to change. That one was down by 29, right? So I'm taking away 29 worth of, pulling to this direction. So I'm going to have to move this down by 29. So what's 212 minus 29? Okay, 212 minus 29, 183. So is 183 a prime number? Well, if you add up the digits, it's divisible by 3. So this is still not a prime number. So we're going to have to take out something else. Again, we could try 29 again since it's the ones that'll move it the least. We want the highest possible number here. So if we get rid of 29 also, that's going to bring this 183 that we had down by another 2. It's going to bring it down to 181. Now is 181 prime? Let's see, 181, if you add up the digits, it's not divisible by 3, it's not divisible by 5. You can do the 7 rule, or you can just use your calculator. It's not divisible by 7, not divisible by 11, not divisible by 13, and yeah, we've gone to the square root at that point, right? It's not divisible by 17. We're good. That one's a prime number, so that is going to be the 1. And what did they ask for? It said, what is the greatest prime number that can be in the set? Okay, that's it. That's it. 181. Great. So 181 is going to be our answer there. 181. All right, let's move on to the next one. We only got 3 more left. Rosencrantz has a bag containing 10 fair coins, 9 of which have a head's face and a tail's face, so they're normal coins, but 1 of which has 2 heads faces. Okay, that's a trick coin. Guildenstern, and this is a reference to, there's a movie, Rosencrantz and Guildenstern Are Dead, where at the beginning of the movie this guy flips a coin about 30 times and it lands head every time. Guildenstern randomly draws a coin from the bag, then flips it 10 times and notices that it comes up heads each time. What is the probability that the coin he drew is the one with 2 heads faces? Express your answer as a common fraction. Okay, so what we have to do is we have to say, what is the probability that he draws that trick coin and then he flips 10 coins? So trick, we have the probability that he gets the trick one and then flips 10 heads, right? So head, dot, dot, dot. Divided by that probability, well, let's just call that probability the trick, and then divided by that one that he draws the trick one and does all the heads, plus the probability that he draws a non-trick one and then gets heads, 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 heads. So we need to compute those 2 probabilities. Let's take a look at that. So first of all, the probability that he draws the trick coin is just going to be 1 over 10 because there's 10 coins. And then the probability that it lands heads is going to be 1 every time, right? So they're just multiplying by 10 ones. It's still just going to equal, dot, dot, dot. This is just going to be 1/10. Now the probability that he gets heads every time after drawing a non-trick coin. First of all, he has to draw a non-trick coin, which is 9/10. And then he has to get a heads every time. So that's a 1/2 chance the first time, times a 1/2 chance the second time. And we're going to have 10 of these. We're going to have that dot, dot, dot. That's going to equal 9/10 times 1 over 2 to the 10th, which is 10/24. All right, so these are our 2 probabilities. We have to take, if this is probability 1 and this is probability 2, what we want to compute is probability 1 divided by probability 1 plus probability 2. Because what it's asking for is, it's saying that this happens. We don't know whether it's this one or it's this one, but one of these 2 things happened. And you want to know that given the fact that one of these 2 things happens, what is the chance that it was this one and not this one? So what we have to do is we have to take this probability divided by the sum of those 2 probabilities. Okay, so since we're taking the ratio of these, well, they're all divisible by 10, so maybe I'm just going to multiply these all by 10 since I'm taking a ratio. This will be 1 divided by 1 plus 9 times 1 over 10/24. Okay, now it's just some simple arithmetic. So 1 can be written as 10/24 over 10/24. If we add 9 over 10/24, we're going to have 10/33. So this is going to be 1 over 10/33 over 10/24. And of course, that's just a reciprocal. That's just going to be 10/24 divided by 10/33. So if that guy flips 10 coins, it's quite likely that he got the trick coin and not one of the regular coins, right? It's 10/24 over 10/33. They want it as a common fraction. Yeah, I think this is a common fraction, right? Because the only prime factors of 10/24 is 2, and 10/33 is obviously not divisible by 2. So that's our final answer there. We got 10/24 divided by 10/33. Okay, 2 more to go. Probably going to be the hardest ones. This one says, how many positive integers less than or equal to 1,000 can be written as the sum of an even number of distinct powers of 3? Okay, let's start by writing all the distinct powers of 3 that could be used. You could have 3 to the 0, which is 1. 3 to the 1 is 3. And so on. We've got 9, 27, 81, 243, and 729. And if you go any higher, you're already going to be larger than 1,000. So we don't need to go any higher. Now it says we need to take an even number of these and add them up and find how many ways we can do that and get distinct positive integers. So first of all, there's no way you can add 2 different sets of these up to get the same number. And the way I think about that is that basically any number that you get by adding up some set of these would be a number written in base 3, because in base 3 you have a ones digit, which is a 3 to the zeros digit, you know, and then you have a 3 to the ones digit, which has a space for that, and you have a 3 to the 2 digit, which is here, and you have a 3 to the 3 digit, which is here, and so on. And when we take some set of these, we're basically going to get up to a 7-digit number in base 3, right, with ones and zeros. So we might, if we pick, for example, if we pick these 4 numbers, the 729, so we pick the 3 to the, let's see, what is this? This is 3 to the 4th, 3 to the 5th, 3 to the 6th. So if we, this one is our 729's place, this one is our 81's place, this one is our, what is this one? Our 9's place and our 3's place. When we, you know, this number in base 3 is going to be what we get by summing up this number and these two numbers here. And so it's obvious that we can't get the same result by picking a different set of numbers, because that would mean there would have to be 2 different ways to represent the same number in base 3, which is not the case. So that's one way to think about it. There's probably easier ways to think about how it's never going to get a duplicate number. But we have to figure out how many of these there are. So there's 7 total numbers. So if we want an even number, we could have 2 of them, we could have 4 of them, or we could have 6 of them. So let's just start by thinking about how many different ways can I pick 2 numbers. So that would be 7 choose 2. 7 choose 2, which is just 7 times 6 divided by 2, which is equal to 21. Now, are any of these 21 numbers, by picking pairs of these, going to be greater than 1,000? Well, the biggest one is going to be when I pick these 2 numbers, 243 and 729. That's going to be 972. It's still not greater than 1,000. So all of these are legit. We can take all 21 of those. They all count. What about when we pick 4 numbers? Well, first of all, how many are there? If you pick 4 numbers, there's 7 choose 4 of these things. So what is that? That's going to be equal to 7 times 6 times 5 divided by, let's see, 7 times 6 times 5 divided by, let's see, we've got 7 factorial divided by 4 factorial, 3 factorial. So 3 factorial down here is going to be 3 times 2 times 1, which is 6. So this will cancel with this, and we'll just get 35 of these things. But we have to check to see if all 35 of those are less than 1,000. That's going to be a little tricky. Well, I'll come back to that. I'm not going to put a box around this yet. What about if I have 6 numbers that I pick? Well, let's see. How many ways are there to choose 6 of these 7 numbers? So that'll be 7 choose 6. Let's see. Am I doing this right? So 7 choose 6. Oh, well, that's just the same as 7 choose 1. That's just going to be 7. There's just 1 to exclude, right? There's just 7 of these. So I'm just choosing 1 to exclude. Now, which ones of those are going to be greater than 1,000? Maybe what we ought to do is just add up all these numbers and see how much we have to exclude from all those numbers in order to be less than 1,000, or less than or equal to 1,000, it says. So we've got 1 plus 3 plus 9 plus 27 plus 81 plus 243 plus 729. That's going to give us 1,093. So we have to exclude at least 93. How many positive integers are less than or equal to 1,000? Yeah, so if we exclude 93 or more, we're good. But what that means is if we pick any of these 5 numbers to exclude, so in other words, we're going to keep 6 of them. If the one we throw out is any of these 5, we're still going to be greater than 1,000. So out of these 7, we're only going to have 2 of them that count. The ones where we exclude this and the one where we exclude this. Okay. So we've got 21 plus 2 is 23 possibilities, and now we have to figure out how many of these 35 are going to count. Okay, so maybe what we can do is break it down based on what the highest number is that we pick, or maybe the highest number that we exclude. Because what we really, it's probably easier to think about adding up the ones we exclude, because we need to exclude at least 93. So we're excluding 3 numbers, and we need those numbers to add up to at least 93. So how many ways can we pick 3 numbers and have it add up to at least 93? Well, if the highest number that we exclude is 729, we're golden, and we're fine. If the highest number that we exclude is 243, we'll be fine. If the highest number we exclude is 81, what's going to happen? So let's see. Let's say the highest number that we exclude is 81. That means the other 2 numbers are from down here. Now, if one of them is 27, that's going to be fine because we'll be over our 93 total. We need, with 81 out of our 93 accounted for, we need another 12. We need another 12. So we can either get that by picking the 27 or by picking the 9 and the 3. So let's see. So maybe I should think about how many ways are not going to work. How many ways are, yeah, how many ways can I pick it so that the sum is less than 93? So the sum of these 2 numbers is going to be less than 12. Well, 9 and 3 are going to be exactly 12. If I do that, I'll have my 93, I'll get exactly 1,000, which actually counts. So I'm not going to count that one as one to exclude. So 9 and 3 is not good. So basically it's going to have to be 1 and 3 or 1 and 9. Those are my 2 possibilities. So I'm going to take this 35 and I'm going to subtract 2. I didn't subtract any for the case where this was the highest number I excluded or where this was the highest number I excluded. But for the case where 81 was the highest number I excluded, I subtracted 2. What about in the case, let me maybe clear up some of these things here. Oops, I shouldn't have cleared up my -2. What about in the case where 27 is the highest number that I excluded? So I'm excluding 3 numbers, and I'm saying the highest one is 27. Well, basically, I can pick any pair of these 3. So 3 choose 2, there's 3. So I'm going to subtract 3 for that, because I can pick 9 and 3, or I can pick 1 and 3, or I can pick 1 and 9. Either way I do it, it's going to add up to less than 93. The ones that I exclude are going to add up to less than 93. So those are ones that I want to subtract. Oops, let me write back down my -3 here. Now I'm going to move to the case where 9 is the highest number that I'm going to exclude. And in that case, it's going to have to be these 3 numbers that I exclude. I don't have any wiggle room, so I'm going to subtract that one as well. So that gives me 35 minus 6, which is equal to 29. I can put a box around that one now, and I just have to add these 3 up. So we have 21 and 29. That gives us 50, and 2 is 52. There's 52 numbers. So that's our final answer. Okay, we're on to the last problem. This one says, in concave hexagon A, B, C, D, E, F. Okay, so it's a hexagon, but it's concave because you can see there's a line here that connects 2 points inside the hexagon, but the line segment is not contained within the hexagon. It says segments A, B, and E, F are parallel. Okay, A, B, that's this one, is parallel to E, F. Okay. And it says segment B, C, and D, E are parallel. Okay, so maybe I'll draw 2 arrows here and 2 arrows here. That means this line is parallel to this line. And then it says measure angle A plus B plus C is 270. Okay, so if I take this angle, and I add this angle, and I add this angle, that's 270 degrees. Okay, what is the area of the hexagon? Alright, so this was a tricky problem. One thing that I'm going to do here is I'm going to extend segment CD. So I can extend segment CD up to here, and I'm going to extend segment AF as well. And if I do that, I'm going to get another point where those 2 intersect, right here. And let's just call that point, I don't know, A, B, C, D, E, F, let's call it G. Okay. And the reason I did that was because I had these 3 angles adding up to 270, and it just seemed like, you know what, I should make a quadrilateral out of that. And now the remaining angle is going to be 90 degrees, because 270, you have the sum of the angles of this big quadrilateral is going to have to be 360, because every quadrilateral has that. So that's going to be a 90-degree angle, which is kind of nice. Alright, so Yeah, so what's next here? So one thing is that I've now got two quadrilaterals actually. Not only did I make this big quadrilateral, but I also made this smaller quadrilateral here. And the thing about it is that because these lines are parallel, I have some corresponding angles now. So for example, this angle corresponds to this one. So those have to be the same angle. And I also have this angle is now corresponding to this angle, so those also have to be the same angle because these are parallel. And since these three angles are the same as these three angles, that means this angle is going to have to be 360 minus that, and it means this angle is also going to have to be 360 minus that. So this angle is equal to this angle, and this angle is equal to this angle, and this angle is equal to this angle. So now I have these two quadrilaterals as similar quadrilaterals. And I can start to think about, okay, what's the ratio between side lengths of those quadrilaterals? And I can either use the 34 and the 51, or I can use the 16 and 24, which maybe is a little easier. And I can immediately see that that ratio, 16 to 24, is just 2 to 3, right? So I've got a 2 to 3 ratio in the side lengths of these quadrilaterals. This is 2 times 8, and this is 3 times 8. This is 2 times 17 and 3 times 17. So now what do I want? I want the area of the hexagon. Well, I guess I can start to try to figure out these other side lengths, like for example from F to G. Can I figure that out? Well, let's call it X, since we don't know it. X is in a 2 to 3 ratio with this length, x plus 9, right? X plus 9. That's going to have to be equal to 2 to 3. So we can cross multiply. We get 2x plus 18 is equal to 3x. If we subtract 2x from each side, we have 18 is equal to x. So that means this thing is 18 here. And actually, that should have been much more obvious to me, right? I could say if this is a 2 to 3 ratio, then I should just be able to cut this in half, and each half should be the length of this. I didn't have to do all this stuff here. That was a little silly. So I could just double this side length to give me this length. And let me just do the same thing over here. Since this is 12, I can double this side length to get, I can basically say this is made up of 2 12s, which is 24. And now I've got a right angle here, and I've got these two sides 18 and 24 as legs, so I can make a right triangle out of that by extending D, by making a line that connects D to F. Okay, that gives me a hypotenuse right there. So I can compute the length of that hypotenuse, I suppose. Because I've got 18 and 24, that's 6 times 3 and 6 times 4, so I should have 6 times 5. It's a 3, 4, 5 triangle. 6 times 5 is 30, and this triangle here is going to be an 8, 15, 17 triangle, which means it's also a right triangle, because 8, 15, 17 is a Pythagorean triplet. So that means this is also a right angle, which is great, because we want to be able to compute some areas, and all we have so far is side lengths. So it's nice to be able to have some right angles so that we can compute some areas. So I can compute the area of this triangle here. It's just going to be 18 times 24 divided by 2, which is just 18 times 12. I'm just going to be lazy and we'll do it this way. 18 times 12. That's going to give me 216 here, 216. And the other one will be 16 times 30 divided by 2, which will be 30 times 8. I can do that one in my head, 240. So the area of this quadrilateral is the sum of the area of those two triangles, and that's going to be 456, right? 456. Now, that's actually the part that we don't want to know the area of, right? I mean, if you think of this big quadrilateral, we want to know everything except for the small quadrilateral. That will be our hexagon. So what we can do is say, all right, I know that these similar hexagons, they need to have area ratios that is a square of the side ratios. So the area is going to be in the ratio of 4 to 9. And that means that this is 4 to the big quadrilateral. That big quadrilateral will be 9/4 of this. And then we're going to have to subtract off this. So that means this part, the part that we're looking for, is going to be 5, I might have said that wrong, 9/4 of this. Yeah, it'll be 5/4 of this. So we can just take 456 and multiply by 5/4. So that should give us our final answer. All right, let's do that. So we got 456 times 5 divided by 4. That gives us 570, which is the correct answer. So that's the end of that. And I hope you guys enjoyed that video. We'll just put the answer 570. And we've gotten through the team. We did the target. We did the sprint. So I'll put links to those videos in the description and hope you guys enjoy them. All right. See you next time.